I think some of you already heard the announcement from a previous class about the technical conference tomorrow, but in case you hadn't, I wanted to point it out that it's being held tomorrow over in the Student Center. And it starts with free food from 8 to 8:45, and then it pretty quickly gets into technical subjects, and there are a variety of interesting presentations here, and I think the one that maybe is the most applicable to a course in hydrology is this presentation at 3:20, which is having to do with some spillway modifications. It's a presentation by folks at the Dam Safety Modification Center. So as you're available, I'd encourage you to participate in that tomorrow. I think it'll be a good opportunity to both learn and also network with people who've graduated from our program, employers. So I'd encourage you to check it out. You've turned in already homework. This isn't right. It's homework 2. You've turned in homework 1, and the second assignment is just 2 problems, but it's due on Monday, so you don't have a whole week to solve that one. Both of the problems are related to some ways of estimating evaporation. So I think you can get a good start on that assignment after the examples that we'll work through in class today. So I'd encourage you to look at that sooner rather than later. The evaporation stuff that we're talking about is in Chapter 7 still of our textbook. And obviously there's a lot more to evaporation than we'll have a chance to just scratch the surface on today. So I think it's important and valuable that you read the text and see the other way to explain things that our textbook author goes through. So we talked about precipitation already, and evaporation is another important process that both contributes to atmosphere and the moisture for precipitation, but then it also relates to how much water there is for runoff. So ultimately what we're heading towards is ways of predicting runoff, and evaporation, even during a storm event, can have an impact on the amount of runoff that occurs. So we're going to start by looking at a couple of videos, just because I think sometimes observing something helps to set the stage for our theoretical discussion of it. And this first video is literally, it's just watching water evaporate. So they say, there's nothing as boring as watching paint dry. People who say that have never been to a soccer game before, but sorry, just joking, sort of. But watching water evaporate, I think it does. All right, let's look at this and talk through what we're seeing. So this is concrete surface, and when it starts out, you can see that there is a section that's already dry, a section that's fully saturated with moisture on the surface, and then sections where the water is going to be retreating towards this part of it. So let's just play it. And interestingly, what we're looking at is partly in a shadow. So, this would be maybe from a explanation standpoint better if the whole thing had the same amount of sunshine. It doesn't, but still, anybody want to speculate why is it evaporating sooner here than in that section?
Is it less deep there?
Yeah, I think that's what it is. I think the concrete probably was laid out at a bit of a slope so that there was a greater depth of water on one side of the slab than on the other. And so just where it is thinner, where there's less water, it evaporates to dry sooner than where the depth is greater. So there are a couple of different factors that influence evaporation. And what you can see is where the sun is. This is a bit of a time-lapse video, but where the sun is, it's evaporating even more quickly than here in the middle where it's still in a bit of shade. So today what we're going to talk about is that solar radiation partly influences how quickly evaporation occurs, and then it's also other factors like humidity and wind movement. So that's the first video, is just watching water evaporate. Now, the Leidenfrost effect is also liquid going to the vapor phase, but this is a pretty fringe case. It's throwing water onto a hot skillet. So in the first case, what was providing the energy to transfer water from liquid to vapor was sunshine, or the temperature of the air, which is itself governed by solar radiation. This, what's providing the heat, is a hot pan. So they're going to pour liquid water into the hot pan, and you see it dancing and sizzling about. It's going from liquid to vapor. And what drove it there is an abundance of heat. So we know that temperature plays a role in evaporation. This is another interesting contrast of, in Yellowknife, Canada, they've got even colder weather than us. I mean, I feel like we're suffering. I checked the thermometer this morning, and for some reason my thermometer got stuck in SI units. There's some series of button pushes you have to go through to get it back into Fahrenheit, but I don't know what that is. So right now, this morning, my thermometer said, I think, -9 Celsius when I looked at it. This is -30 Celsius, so a lot colder than we've been experiencing in Huntington. But what she's going to do is take boiling water from a kettle, pour it into a dish, and throw it into the air. And it just kind of immediately goes into vapor. There's such a contrast in the heated water and the really dry air. I mean, part of this, what we're seeing is that, remember that the solubility of moisture in air decreases with decreasing temperature, and so the air that she's throwing it into is very, very dry. There's not much moisture in it, and so the fact that the water is itself so warm and the air is so dry allows it to vaporize even before the droplets hit the ground. Kind of an interesting effect. I've tried the same thing here when it's been really cold before, and if it's cold enough, you can get a similar thing. And then the last video we're going to watch is water vaporization, but in the absence of heat. This is just kind of a fringe case where, let me turn the audio on. First I'll pause the video. Okay, so here a glass of water is under a vacuum bell, and they're using a pump to suck out the air that's inside of this chamber. And normally when you have a glass of water just in atmospheric air, the air pressure is acting down on the surface of water, and there is some vapor pressure which varies depending on the temperature of the water. You know, when the water is room temperature, maybe the vapor pressure is relatively low, but then as you increase the temperature of the water, the vapor pressure is increasing until when it matches the atmospheric pressure, that's when boiling occurs. But in this example, they're not adding heat to increase the vapor pressure of the liquid. What they're doing is they're sucking the air out of the bell, reducing the atmospheric pressure, and then when the atmospheric pressure, which is resisting vaporization, when it's equal to the vapor pressure of the liquid at whatever temperature it was, then that's when the boiling occurs. So just the fact that you're seeing boiling doesn't necessarily mean that the water is warm. It just means that the vapor pressure is equal to the atmospheric pressure. So you can either make those two things equal by increasing the temperature of the water or by decreasing the pressure of the atmosphere that's acting against the water. So that's what this one's doing. So interesting fringe case there. We don't often see reductions in vapor pressure causing boiling except in the case of cavitation. Cavitation happens on boat propellers or sometimes through like pipes that take water through a dam. If they have very high velocities, then the pressures can be reduced so that the pressure is as low as the vapor pressure of the water, and then cavitation can cause damage sometimes to these high velocity water pipelines. So these are all just illustrations of different things that is causing a transition of liquid to vapor. And we're going to talk more about ways to calculate the rate of evaporation. And a big part of evaporation is solar radiation that comes in, from outer space, from the sun, through the atmosphere. Some of it passes through the atmosphere. Some of it is going to be reflected by gases in the atmosphere. Some of the solar radiation is going to be reflected off of clouds back into space. Some of the solar radiation will come and be reflected off of the ground surface, like the ice caps, for example, have a really high rate of reflection of radiation back into space without it being absorbed. But some of the radiation will be absorbed before it is emitted back out into space. But this diagram just illustrates the different wavelengths of radiation that's coming in. The incoming solar radiation is relatively short wavelengths in the ultraviolet and visible range. And then the energy that's emitted out into space is typically long wave radiation in the infrared range. This figure illustrates the relative quantities of radiation that's coming in. And so when the sun is shining on the Earth's surface, if we have 100 units of solar radiation that's coming in, and that's generally measured in units of watts per square meter, some of it will be backscattered by air, meaning that it's, before it gets to the surface, reflected back to space, and it hasn't changed from shortwave to long wave radiation. Some by clouds, some by the surface, but about, it's showing here, 30 units of incoming solar radiation will be reflected, whereas 70 units would be absorbed and then reflected again later. So all of the incoming solar radiation goes out again. If we have 100 units coming in, 30 units will go back out to space as shortwave radiation. The other 70 units are emitted as long-wave radiation. There's not an accumulation of heat in the Earth's atmosphere. If there was an accumulation, then that would mean that our temperature would be increasing steadily. And while it is increasing steadily, it's for different reasons than an accumulation of solar radiation. It's because over the years there's an accumulation of greenhouse gases, which is very gradually increasing the average temperature of the atmosphere. But on an annual basis, the amount of incoming and outgoing radiation are the same. The important thing to keep in mind, though, is that it's this long wave emission of radiation that is closely tied to evaporation of water. And so the water absorbs this energy, and then in the process of evaporating, it's using the energy. It's the energy that comes in from the sun is driving the process of vaporization. And there's a quantity called the latent heat of vaporization that tells us how many joules of energy are required per kilogram of water to cause that evaporation. I think everybody's probably familiar with the idea that the sunshine is more intense at the tropics, and this figure does a good job explaining why that is, because if the sun is over here off the screen shining its rays in a straight line towards the Earth, some of those rays are projected over a larger area at the poles. And so there's incoming solar radiation, like 1 square meter area that's coming in from the sun, maybe would be projected over more than 1 square meter because of the curvature of the Earth. And I've definitely felt that before. If you're in Florida, if you visited Florida before, you can kind of get the sense that you maybe are going to burn more quickly because the solar radiation is more intense. I've been to Kenya, which is right on the equator, and the sun was definitely more intense there. And of course, it varies seasonally as well. We know that during the winter months, for example, here in the northern hemisphere, there's not only fewer hours of daily sunshine, but also the radiation intensity is less. If you go outside during the winter time, you're unlikely to get a sunburn, both because it's cloudy, but even on a sunny day, you're not likely to get a sunburn because the sun is lower on the horizon. It's not overhead and coming at you directly. When it's low on the horizon, then more of the radiation is reflected off of the atmosphere, and also it's projected over a larger area. And so there's just on the ground surface area less energy during the winter months than there is in the summer months because of those two effects. the enhanced reflection during the winter months, and then also the greater area over which the radiation is projected. This is a map of the average relative humidity in the United States, and it's more or less what you'd expect if you've traveled. The humidity is higher in coastal areas and in the Midwest, and in the deserts of the western United States, the humidity is very low. Humidity is water vapor. It's moisture that's dissolved into air. Air without humidity would be a mixture of nitrogen, oxygen, some noble gases, and carbon dioxide. But because of the kinetic energy that exists in air at temperatures like the temperature that we've got in this room, there's a certain amount of moisture that's bouncing around in the gases in the air along with the nitrogen and oxygen. There's H2O that exists as a gas because of the energy that is supplied and available to that gas to stay in the solution, the solution of gases in this room. Not every molecule has the same amount of kinetic energy. There's collisions of gases that transfer some energy so that there's a distribution of energy among the particles in the atmosphere. And there's also an exchange. Moisture that's in the air may condense, and there would be evaporation. Like if we had a big pan of water in the classroom here, some of the water in that pan would evaporate into the air, and some of the moisture in the air would condense into that pan of water. So there's a constant exchange between the liquid phase and gas phase, because the water in the pan in this room would also be at the temperature of this room. And so some of the particles in that liquid phase would, through a series of consecutive collisions, get enough kinetic energy to escape out of the liquid phase and turn into a vapor. So heat and sunshine are what drives the evaporation. And if we look at the molecular level, we can think about a certain fraction of a liquid existing in the gas that's above it. So this is the interface of the liquid and the gas. So this is all water, and the water molecules are moving around and colliding with each other. And so there may be this molecule that's just has enough energy accumulated to evaporate and join the other gases that are in the gas phase, and another molecule which may be condensing into the liquid. And we can measure the quantity of gas above the liquid layer in terms of the pressure of the atmosphere, or the pressure of the gas. And so that maybe is in pascals or atmospheres or psi. And the quantity of water that is in the atmosphere, we could measure that as a partial pressure. And if you remember back to chemistry, when you have mixtures of gases, if the overall atmospheric pressure, let's say, is 760 millimeters of mercury, one way to express how much of each gas is in there is by its partial pressure. And so if it's 80% of the atmosphere is nitrogen, then it could be that the partial pressure of nitrogen is maybe 650 millimeters of mercury. And then the partial pressure of oxygen is 100 millimeters of mercury, and so on. So partial pressures is one way to measure the quantity of gas in the water vapor that's in the atmosphere. Another way we could measure it is relative humidity, which is a fraction of the amount of water that's there compared to the maximum amount of water that could exist for a certain temperature. So we'll look at both. We'll look at partial pressures and also relative humidity as we're estimating the rate of evaporation. And so keep in mind that the cause of vaporization is energy exchange. And over the surface of the Earth, if we take into account desert areas that are very warm and dry, polar areas that are very cold, even though they may have a lot of moisture, and more moderate climates in between, over the surface of the Earth, the average amount of evaporation is 3 millimeters per day. And there's a related phenomenon to evaporation called transpiration, which is when plants are emitting water directly from the plant into the atmosphere. And we're not talking about transpiration today, but it is something that's important. It's a source of humidity and a source of water vapor in the atmosphere. Sometimes the two are combined together and called evapotranspiration, where you're taking both the evaporation from liquid water, evaporation from moist soil, and then combining it with the amount of water that's lost by plants to the atmosphere. Now here's that statistic that I mentioned earlier. It's a physical constant that tells us the amount of energy that's required to drive water from the liquid phase into the gas. And so the latent heat of vaporization says that there's a certain amount of joules per kilogram of water that's required to undergo that transition from liquid to gas. And it varies slightly depending on the temperature. And here the equation is written with the temperature being expressed in units of Celsius. So it's mostly a constant, but if the water is warm rather than cool, then that reduces the latent heat of vaporization a little bit. As you might expect, that liquid molecules that are near boiling don't need as much energy to go that extra amount into the vapor phase than liquid molecules that are cool and maybe closer to freezing. So there's more energy required for the cooler liquid. But we'll use this constant in calculating how much evaporation is going to exist when we provide a certain amount of energy. So joules, the energy that's provided to drive evaporation, is provided by the sun. And so we're going to be asking how much energy is coming in from the sun to be available to drive evaporation. And for the homework assignment, what I've asked you to do is look at some measured evaporation data and compare it to evaporation data that you can calculate based on some sunshine data from New Mexico. There are these different stations across the United States where they measure the sun every day. And in fact, they measure it every hour of every day. And so there's a file that I've just put on Blackboard today that is for a certain location in Santa Fe, New Mexico, the hour-by-hour solar radiation data for the year 2005. So I'm asking you to look at a certain day in 2005 and predict how much evaporation could occur during that day based on the sunshine that was available. And when you know how much sunshine is available, then you can combine that with the latent heat of vaporization and estimate the evaporation amount. The sun is providing the energy. This constant tells you for a certain amount of energy how much evaporation is there. Anybody recognize what we're looking at here? Any guesses? Yeah, that's the Ohio River. Good, exactly. I was driving on Route 2 and took a picture. I couldn't resist. Although you're not supposed to play with your phone while your car's in motion. Just only that one time is the only time I've ever done that. And I took a picture because you'll notice that there's clouds over the river. So why would there be clouds just over the river? It's not for the reason that you might initially think. I mean, initially you might think, well, clouds are water, the river is water, so the clouds are over the river because it was water from the river that made that cloud. And that's actually not it. It's because the river provides a temperature difference. That's why that cloud is forming above the river. It's because in the fall, the air loses temperature more quickly than the water does. Like water stays warm through the fall, or relatively warm. Like you could jump in a pond in September, and even though the temperature outside maybe is 45 or 50 degrees on a cold September day, the water could still be in the 70s because water cools off very slowly. So on this day, the water was relatively warm and it was emitting heat. And as it was emitting heat, it was warming up the air. And remember that warm, moist air, as it rises, begins to condense and form clouds. And so that's what happened, is that there was some rising that was caused by the lifting that occurred through the heat radiating off of the river.
Just to add on that, what you're talking about, like in spring and fall, when it's fog and still at the time when it still freeze out, like get frost in the plants can actually survive if it's planted close to the river like that, because similar effect happens. So the air's make it freeze from frost, but
Yeah.
and keeps it warm.
Yeah, it's like a little microclimate. Absolutely. So it's a heat source. And eventually it'll get cold. It'll lose all of its heat eventually. But I thought that was just an interesting illustration of the relationship between warm, moist air and cloud formation and evaporation. And all right, so here's a series of equations. It looks complicated, but it's actually way more complicated than it looks. So what we're looking at is like a laughably simplified approach to how much energy it takes for evaporation. It's probably like in all the stuff I've ever done research-wise, one time I had a project for the Department of Environmental Protection here in West Virginia, and part of the project I was doing a water balance for a watershed out in Greenbrier, near the Greenbrier, and so I was having to do stuff like this, like estimate how much evaporation there was based on solar radiation data. It's really, really tricky and complicated. So I think we can get through this, but I just want to give the disclaimer that for the people who are like really into evaporation estimation and modeling the amount of energy that's required and stuff, this doesn't capture all of the complexity of the natural world. This is just kind of a quick approach for estimating how much evaporation there is. All right, so what it's saying is that we want to keep track of how much heat is flowing in to a certain quantity of water. And the energy balance method assumes that the rate of heat input is going to be related to the rate of evaporation. So we just need to basically account for things like the incoming solar radiation, R sub I. This alpha is going to be how much of the incoming solar radiation is reflected off of the water surface. And then we also need some means of estimating the amount of emitted radiation, so R sub E. And we can estimate that based on the temperature of the water. The temperature of the water will give us an idea of how much energy it's radiating back to space. And so the difference between the two, the difference between the incoming radiation that isn't reflected, so 1 minus alpha is the amount of radiation that didn't get reflected back to space. So that's the amount of radiation that went into the water, and then the amount of radiation that's emitted. The difference between the two, the net radiation flux in terms of watts per meter, is how much we can say is available to drive the latent heat of vaporization. So this formula down at the bottom here, E sub R, it's the evaporation rate, which will have units of length per time, and it's based on the net energy that was provided to the water, the latent heat of vaporization, and then water density. The units all work out that way to where we'll end up with length per time. So just to give you an idea of how this works together, let's say that we had a water source. The Khalid Lagoon is in the UAE, near where I used to live. And if during a certain day the incoming radiation was 978 watts per meter at noon, then we'd want to know the water temperature to be able to estimate the emitted radiation. Later, for a related example, we're going to want to know the air temperature, humidity, and wind speed. Although for this first example, we won't use any of those factors. We'll just use the radiation that's coming in. A typical albedo, which is the reflectivity of water, is about 35%. So of the solar radiation that comes in, about 65% will be absorbed by the water, 35% will be reflected. That's why if you're swimming, sometimes you don't get as bad a sunburn as if you're just laying out on the beach, is that the water actually does protect you a little bit because of the reflection of water off the surface. The radiation emissivity constant, we'll use that in trying to estimate the outgoing emitted solar radiation based on the temperature of the water. And that also depends on the Stefan-Boltzmann constant. These are two constants that we're going to put in the water temperature in Kelvin, and then coming out in terms of watts per meter squared is how much energy is being radiated by the water for a given temperature. So remember, long wave radiation, if you've ever, let me explain it this way. Have you ever walked in front of a brick wall after sundown and you can still feel the heat coming off of that? You can feel it even if you are, 4 or 5 feet away from the brick wall. It's not convection that you're feeling. You're not feeling like warm air. You're feeling long wave radiation. It's being emitted. So it's kind of like an infrared sauna, if you've ever been one of those. Its energy is going through the air, not being conducted by the air. So in this formula at the bottom here, R sub E is the emitted energy, which is based on the temperature of the water. We can estimate it that way. All right, so the calculations here, if I just put a few things up on the whiteboard, let's try and determine the evaporation rate in millimeters per day using this energy method. Now this energy method, take in mind, these equations do not do anything with the humidity of the air. These equations so far don't do anything with the wind speed. And as you may guess, those actually do have an effect, but we're ignoring those for now. This energy method just assumes that the limiting factor is the amount of energy that's being provided to the water to drive evaporation. So the first thing we'll need to know is the temperature of the water in terms of Kelvin. 26 degrees Celsius plus 273.15 equals 299.15 Kelvin. So we know the water temperature, the amount of radiation that's emitted by the water is E sigma T sub P time to the 4th power. So that is 0.995 times 5.67 times 10 to the minus 8th watts per meter squared times Kelvin to the 4th, and then we do 299.15 Kelvin to the 4th power. So the amount of radiation that's being emitted is 451.8 watts per meter squared. That's just energy that the water is sending back out into space at this moment in time, at noon on February 12th. Let me, by the way, bring these calculations up on the screen so that if anybody is revisiting the video later on, you'll be able to see that. So we've calculated the water temperature in Kelvin and the amount of radiation that's emitted from the water. Okay. Next, how much radiation is available to drive evaporation? So R sub n, the net radiation that's available, it's the incident radiation times 1 minus alpha minus R sub E, the emitted radiation. So the radiation that was coming in was measured at 978 watts per square meter, and only 65% of that isn't reflected. So 1 minus alpha tells us how much isn't reflected, and then we have to subtract out the radiation that's emitted to space because we're replacing that amount that is long wave that's going back out due to the water temperature. So the net radiation that's available is only 183.9 watts per meter squared. So of the 978 watts per meter squared that comes in, this is how much is available to drive evaporation. And for the temperature that we're dealing with here, the latent heat of vaporization, 2.501 times 10 to the 6th minus 2370 times T. And the temperature we need to put in terms of Celsius, and it is the air temperature that we use, 28.5 degrees Celsius. So that is 2,433,455 joules per kilogram. So that's how much energy is needed per kilogram of water. And the units of joules per kilogram, that's the same as watt seconds per kilogram. Okay, so let me refer here to the handwritten notes here. So we've calculated the net radiation and the latent heat of vaporization. For the density of water that we have here, for the typical water temperature, density is 996.3 kilograms per cubic meter at this temperature. And so the final equation that we're going to use is this one to calculate the evaporation rate. So E sub R, E sub R is the net radiation in the numerator, 183.9 watts per meter squared. The latent heat of vaporization, 2,433,455 watt seconds per kilogram. And then the density of the water, 996.3 kilograms per cubic meter. That's what we'll get. The units here are meters per second, because remember, joules is watts per second, so the time units come out of the joules, and if we cancel out all the like units, then it's 7.57 times 10 to the minus 8th meters per second. So that's how quickly water is evaporating. It's too small to be anything other than abstract, so if we convert that into how many millimeters per day, what we'd do is we'd multiply by 86,400 seconds per day, and then multiply by 1,000 millimeters per meter, and that 7.57 times 10 to the minus 8th meters per second of evaporation, that's suggesting that if this same intensity occurred over an entire 24-hour period, then there would be 6.54 millimeters per day. This is just an instantaneous evaporation. This is the evaporation rate at this moment in time. So if we wanted to know how much evaporation actually happened during the day in question, what we'd need to do is we'd need to measure the solar radiation maybe on an hourly basis, and then do like a numerical integration where we'd say, well, it was this evaporation rate for 1 hour, then the sunshine went down for the next hour, and we'd find out the evaporation rate during that period, finding the depth of evaporation that occurs on an hour-by-hour basis. But this is evaporation rate at noon when the sun was high in the sky and the radiation was 978 watts per meter. So this energy method just says, let's ignore the humidity, let's ignore wind conditions, and let's just look at sunshine, because we know that sun is an important driving factor for overcoming the latent heat of vaporization. So any questions so far on the energy method? So it's a simplification. I've hinted at that pretty emphatically, and what's missing from the energy method is transport. It's like, where does the water go after it is evaporated? It's just assuming that all you need is the energy and then it can evaporate. When the truth is, the water is going to evaporate and then it has to go somewhere. Because if it doesn't go somewhere and it's very humid just above the water surface, like 100% humidity, if it's fully humid above the water surface, then no more water can escape. If the water is fully saturated in a thin film above the water surface, if it's fully humid, then there wouldn't be the capacity to absorb anymore. And so another important limiting factor on the rate of evaporation is accounted for in the aerodynamic method. And the aerodynamic method looks at things like relative humidity and wind speed and takes into account how quickly the water is transported away from the water surface. So this is just showing a control volume approach where we say there is dry air entering a control volume, and one of the control surfaces is at the liquid surface, so that liquid water is evaporating and we've got dry air coming into the control volume and it's carrying out the moist air. And in order to have further evaporation, there has to be something that's bringing the air towards the water surface that is able to absorb more water. So the energy method is basically saying it's pushing the water, and the aerodynamic method is pulling it. You know, something to cause the evaporation and some way to move it away from the liquid surface. And so the driving force in the aerodynamic method is just the difference between how much moisture is in the air and how much moisture it could accept. Because like, remember that concrete video that we watched? On a really humid day with no wind, that water would evaporate more slowly than it would on a breezy day or on a day where the humidity is quite low. Like if we go back to this map, when I run in the mountains of Colorado, that feels very different than running in the hills of West Virginia. Like in the hills of West Virginia in the summer, you're just completely soaked by the end of a run. But in Colorado, your clothes never get wet. I mean, it's just the moisture is carried away very easily because the humidity is so low. And so there's a really quick transport of the moisture, and the aerodynamic method accounts for that. So the driving force is the difference between the amount of water that's in the air and how much there could be. And in the aerodynamic method, we're going to measure the wind velocity at a certain elevation above the water surface. And right at the water surface, the velocity is 0 because of the no-slip condition that you learned about in fluid mechanics, where you can't have something that's stationary and then a fluid flowing over it with a frictionless effect. So the further away you get from this stationary liquid water, the velocity is increasing. And so what we'll usually do is we'll talk about the wind velocity at a certain height above the water surface, like 2 meters above the water surface is a pretty standard location to measure the wind velocity at that location. And the more wind velocity there is, the greater rate of transport of vapor away from the water surface. And another factor is that as we go up through the atmosphere, remember the adiabatic lapse rate is the elevation effect that occurs where air is generally cooling as you go higher up in the atmosphere. And so that's another factor that's related to how much vaporization there can be, is that when you've got big temperature differences between the ambient vapor pressure and the saturation vapor pressure, then that driving force is going to increase the amount of evaporation that occurs. And then large differences in the humidity. The specific humidity means the amount of moisture compared to saturation. Relative humidity is one way of expressing the specific humidity. So it's also a driving force. So low humidity drives evaporation and high wind drives evaporation. So both of those things are accounted for in the aerodynamic method. So the aerodynamic method says the evaporation rate, if we're looking at it from the perspective of aerodynamics, it's saying, let's ignore now the solar radiation part of it. Let's just look at how much humidity and wind play a role. And so in the aerodynamic method, you're looking at the wind speed at a certain altitude. In this case, u sub 2 is the wind velocity up off the water surface, not at the water surface, but some distance above it. And the distance above it is taken into account here in the z2 minus z0, where z0 is the height of the waves or the roughness of the water, like if there are ripples or some kind of undulations to the water because of currents or waves, wind-driven or otherwise. So B is a factor that's related to the wind component of it. E sub AS, you're trying to estimate the vapor pressure, like what would be when the water is completely saturating the atmosphere, what would be the pressure of, like the partial pressure of moisture if it was fully saturated. And then E sub A is our actual ambient vapor pressure, where you're using the relative humidity. And then the driving force is how far away you are in the actual conditions from the saturated vapor pressure. So you'll notice if you have a big difference between E sub AS and E, then that's going to lend itself to a larger evaporation rate. So if you have really dry conditions because the relative humidity is low, then that E sub A may be as low as 0, where E sub AS is how much moisture could be accepted by the air at the temperature that we're at. And so the difference between how much water is there and how much water could be accepted is what determines then the evaporation rate. So since we're running low on time, let me just show you the calculations for this one, and then that'll set us up on Friday to answer the question like, well, then how do you reconcile the two methods? One looking at energy, one looking at aerodynamics. Which one do we pick? We'll answer that on Friday. But let me just take you through the rest of this example where we are using the humidity and the wind speed to estimate the aerodynamic component of evaporation. So in this example, we have all of the same data from before. It's just we're using now things like the wind speed. So we were told in the example that the relative humidity is 75%, the wind speed is 1.7 meters per second, and we're measuring that wind speed 2 meters above the water surface, so 200 centimeters above the water surface, where the waves are 0.3 centimeters. So it's relatively calm. The water roughness height is 0.03 centimeters. So the first thing we do is estimate the saturation vapor pressure. So it's just an empirical equation that depends on the temperature of the air. It's an exponential function. So we estimate that if the air was completely saturated with water, it would have a partial pressure of 3893 pascals. So that's the maximum amount of water that could be in the air. And under a relative humidity of 75%, that means that right now there's 2919 pascals of water vapor pressure. So then we can calculate B using the wind speed and the roughness height. It will have units of millimeters per day per pascal. And then we multiply that by the difference in the saturated and ambient vapor pressure. And according to the aerodynamic method, we can have 2.18 millimeters per day. So then on Friday, we'll reconcile the two. The earlier example that looked at energy was saying 6.5 millimeters per day. This is saying 2.2 millimeters per day. We have some way to split the difference, and we'll look at that on Friday. Just remember that tomorrow is the technical conference. I'd encourage you to participate in that. Enjoy it. And if you have any questions on the homework, you could get started on that right away. Just let me know, and we can talk about it on Friday as well.